Good morning. Our topic today in physics is learning about the weight force in more detail, applying some concepts specifically to something called apparent weight. Your reading should align with this lecture pretty closely, so let's get into it. So the weight force is a type of force that's generated by a gravitational field. And in order to experience a weight force, you need to have a mass in order to experience it. So typically what we do is we draw a free body diagram of an object as a dot, which we'll do a lot in this class. And we'll draw the weight force, which is always going to be pointing down towards the center of the earth. And we'll label that force with a capital W, and the force will be created by the earth on the object of interest. So how do we calculate the magnitude of the weight force? The weight force is equal to an object's mass multiplied by the acceleration due to gravity, which on Earth is going to be 9.8. So let's say I told you that an object has a mass of 10 kilograms. Well, you should be able to tell me what the weight of that object is pretty easily. You would take 10 kilograms. Now make sure the mass is in kilograms. If it were in grams, you'd have to convert it to kilograms. So 10 kilograms times 9.8 meters per second squared. And our answer would be in newtons. So go ahead and do that. So the weight of this object, we would say, is 98 newtons. One thing I want you to do right now is find out what your weight is. It's something that we'll use a lot in this class to do physics scenarios. Now, what forces would you experience? So right now you can take your mass measured in kilograms. So for me, I weigh 165 pounds. I would need to convert that to kilograms. So 165 pounds there are 2.2 pounds in 1 kilogram. So we would, in this case, divide 165 by 2.2. So whatever your weight is in pounds, change that to kilograms right now. So I weigh 75 kilograms, but that's still not really a weight. Notice how I'm using that term incorrectly. It's kind of okay as long as you realize what it really is. And then we'll multiply by 9.8 meters per second squared to get my weight. So my weight is 735 newtons. So let's think for a moment about, roughly speaking, you could take your weight and you could probably multiply it by 5 to get your weight in newtons. So that's pretty easy. What I want to talk about next is this idea of apparent weight. So apparent weight, I'm going to write as weight sub A, or apparent, is what happens when you are now in an accelerating reference frame. What I mean by that is, if I have an object that has a weight, let's say it's me, and I weigh 735 newtons, I might weigh less in some cases if I'm accelerating up or down. And let me explain. But first of all, let me give you the equation here. So apparent weight is the object's true weight. So my true weight was 735 newtons. I'm just standing there. Plus or minus the object's mass multiplied by the acceleration. So if I'm accelerating up or down, that's going to affect my apparent weight as measured, let's say, by a bathroom scale. Okay, so you can go into your bathroom right now, if you're at home, stand on the scale, and hop up and down a little bit, and you know that you can kind of make the scale do some different things, right? So what's going on there? Let's work an example. Let's say that we're still using me as an example. I'm going to put some values into this free body diagram. I'm going to say my weight here now is 735 newtons. Now notice how I'm not doing subscripts anymore. I'm just, when I work problems with free body diagrams, I'm just going to write the values down. And if I'm standing on a bathroom scale, the bathroom scale reports the normal force pushing back up. And it's got to be the same magnitude as my weight because I'm not accelerating. So the normal force has to also equal 735 newtons. So then let's say I jump into the air. So as I'm in the process of jumping, before I leave the scale, I know that I have to have a larger force going back up. So take a moment and draw which of the forces is now going to be bigger, the weight or the normal. Now I'll tell you, the weight can't change. I didn't go on a diet, didn't do any exercise, didn't go to another planet. So what has to change here is the normal force. The normal force has to be bigger. Now I'll draw that as an arrow slightly longer than my weight. Now my weight, I'm still going to say, is 735. But the normal force now got larger. Why did it get larger? Because I pressed down on the scale and the scale pressed back up on me. And I have to apply a larger force than my weight if I'm ever going to leave the ground and jump. So this is going to be some value greater than 735. I don't know exactly what it is. So when we go back to this equation, my apparent weight, that's going to be what the bathroom scale is actually reading. So let's say I told you that the apparent weight in this situation, the bathroom scale bumps up. Let's say it goes to 875 newtons. So what we have here is somehow this, my true weight, which is 735, we added in some extra force to create this apparent heaviness, when in reality it was just me pressing with my legs. So my mass has remained the same. So this is plus or minus ma. In this case, we know it has to be plus because the scale is reading a heavier value. So my mass is 75 kilograms. And the question might be, okay, well, what is the acceleration of the person? So you can solve for that. Take a moment to do that. Okay, so hopefully you were able to figure that out. The acceleration up, in this case, is going to be 1.86 meters per second squared. And that should fit with our free body diagram. If the force is larger pointing up than down, we know we have to have an acceleration taking place. And in this case, the acceleration should point in the direction of the larger force vector, which is up. So this is going to be a positive 1.86 meters per second squared. So let's talk about, well, what actually happened here. As I am pressing down on the spring scale in an attempt to jump, so to speak, what I'm doing is I'm making it feel like I'm heavier, even though I'm not really heavier. My weight has not changed, it's 735 newtons, but for a moment there, that's what the spring scale records, so apparently I did get heavier. Why is that? It's because I'm accelerating upwards at 1.86 meters per second squared. So one thing that I've found that students get confused with in this material is the plus or the minus in the apparent weight equation. How do I know if I'm going to add the mass times the acceleration or if I'm going to subtract the mass times the acceleration? And the best way I've found to teach it is you have to think conceptually about what's actually happening and put yourself in that situation. So a good example to think about might be an elevator. So let's say that you stand in an elevator, the elevator starts going up, and right before the elevator stops, there's that moment as it's slowing down to a stop where you feel lighter for just a second. And what that means is, for a moment, your weight is not your true weight. It was almost as if the floor of the elevator was being lowered out from underneath you as the elevator comes to a stop. And so if you were to take a spring scale, bathroom scale, into that elevator, what you'd see is as the elevator approaches the second floor and comes to a stop, there's a moment there as the elevator is decelerating where you're going to feel lighter. And so if you're going to feel lighter, well, that means the bathroom scale for a moment is going to be reading a value less than your true weight. And the other situation would be heading down. The elevator is going down to the bottom. As it's moving at a constant speed, it should be measuring your true weight. And you have a balanced free body diagram. There's no acceleration. But once our reference frame starts accelerating, our true weight is going to change. It's going to appear to be something else. So think about it for a second. As you now approach the bottom, back to the lower level, the elevator now is going to slow down. And when it slows down, just like it did as we reached the second floor, this time the slowing down is now going to make it feel like you're heavier. Think about it. There's that moment where, as you're coming to a stop, where the direction of your motion is opposite the acceleration. And in that case, you are going to feel heavier, and your apparent weight is going to be something larger than your true weight for that moment. And so if your velocity vector and your acceleration vector are doing opposite things, you're going to get apparently heavier. If your velocity vector and your acceleration vector are doing the same thing, well, you're going to appear to be lighter. An example of this that you might be familiar with is skiing, or even in a roller coaster. As you're coming over a rise, let me draw a picture for you here. Okay, so what I have here is a hill. I have an object moving up over the hill. This could be a roller coaster, it could be a skier, and what happens is, as the object has a velocity vector and comes over the top of the hill, or even if you're in a car, you felt this, you kind of feel that weightlessness sensation. Now, weightlessness is really a phenomenon where your normal force disappears. We always are going to have our weight going down. Typically, we would have a normal force and a weight force that are equal, and you would feel that normal force because your legs have to support your weight. But as you come over a rise here, what's happening is Newton's first law, the object is going to want to keep going in a straight line path, and what happens is the magnitude of our normal force, either between our butt and the seat if we're in a car, our butt and the seat if we're in a roller coaster, or our feet and skis against the snow if we're on skis here, the magnitude of this normal force is going to decrease. And so what we have here is just an apparent weight application where apparently we weigh less than we truly weigh, and that's because of inertia in this case. And so what we could do here is we could use that same equation, the apparent weight equation, to examine this situation. But unfortunately, I've reached my 15-minute limit. I'll make another video.